Entropy and free energy. What is free energy? Well, free energy is energy after some reaction that is now available to do work. So if something happens, we get some energy. Hey, that energy can be used to do something. Now, what is a spontaneous reaction? A spontaneous reaction occurs naturally and it favors the product. Things that just happen. You know, you've heard of someone who's spontaneous. They just let things happen. They just go and do something without thinking. It just happens. And when things are spontaneous, you release free energy. If a reaction releases free energy, it is spontaneous. Entropy is delta S. Entropy is a measure of disorder of a system. Now, the natural tendency of a system is to go toward disorder. Increase in entropy favors a spontaneous reaction. So, if there is a spontaneous reaction, it's because there is more entropy or disorder. If there's more entropy or disorder, it's going to be a more spontaneous reaction. It will just happen. We can observe entropy in nature. Entropy or disorder makes sense. If you think about it, look at your room. If you just let it go, it would become an absolute mess. Look at your yard. If you just let it go, it would go toward disorder. The grass would grow, leaves would grow, just go into weeds. Your room would just have clothes all over it. It's just spontaneous for things just to get messy and disorderly. The disorder, entropy, is natural. If I were just to let my beard grow, you could see that disorder would be spontaneous and just keep going and going. My hair would grow, and even my eyebrows would start growing. It's just natural order. Disorder, it's just spontaneous. This entropy is what would happen. Things will fall apart. But then I put energy into it, and I start shaving. I go against disorder, against entropy, more orderly. I have to put energy into that system. I have to start trimming my hair, trimming my beard. This is totally not spontaneous. There's no entropy here. It's no disorder. Shaving my mustache, and there I go. I look good. We want things to be orderly. We're going to have to put energy into it. We're going to have to get things organized and energized. We have to put energy to get order. If we just let it go in the normal, spontaneous action, it's going to become disorderly. Your room, the yard, your appearance, it'll all just kind of go to heck. So let's look at this diagram here. Here we have a nice orderly system. We have a solid here. This is a solid, and here we have a liquid, and this is a gas. This solid doesn't have much disorder. It's nice and organized. The molecules are structured. But as we go farther this way, the molecules are moving around faster. They're breaking apart more. There's much more disorder. And a gas has an incredible amount of disorder. So we increase as we go from solid liquid to gas. Now here we're going to have an increase in entropy as well. We have an orderly crystal here. We break it up. We have much more disorder, much more disorganization. We have much more entropy. Now the more number of molecules or particles, we have more entropy because they're not stuck together here in an orderly, tight, rigid fashion. We break them apart. It's much more disorder. So we have much more entropy. What about increasing energy or temperature? If we increase temperature, what happens to those molecules? The molecules will move around much quicker, much faster. Things are bashing into each other, much more disorder. Think about if people are running around going crazy. They're, let's say, a big monster's in the room. Everyone's going to start going crazy. People are running around bashing into each other. There's a lot of disorder there. Or as opposed if they're sitting quietly in neat and orderly fashion, that's not much entropy. We increase the concentration, we increase the temperature. That means we're increasing the motion and the molecules, how fast they're going. So they're going to bash more and more into each other. We're increasing the entropy. Every chemical reaction, heat, remember enthalpy, is either released or absorbed. We already know that. And disorder is either increased or destroyed. So, when will things be spontaneous? Enthalpy and entropy will determine if something is a spontaneous reaction. But it's the size and direction of that enthalpy change and entropy change together that will determine if a reaction is spontaneous. So that is whether it favors products and releases free energy. So the combination of enthalpy and entropy, heat and disorder, combination of those two, acting together will determine if it's spontaneous and if it favors the products or reactants and if it releases free energy, energy to do work. Let's look at some examples here. So here we have heat being released, exothermic, and we have entropy increasing. So that's favorable. So we have both of these. If we have heat being released and disorder, we're going to have a spontaneous reaction. That's kind of a no-brainer. Those two things always give a spontaneous reaction. How about in this case? Now, here we have entropy increases, disorder, which is spontaneous and favorable. But here we have heat absorbed, endothermic. That's unfavorable. That means we have to add heat to the system. But we don't add that much to it. The entropy is so much greater than the heat we add to it. So in this case, the reaction is spontaneous. It will be spontaneous. Here we have heat released. So exothermic, that's favorable, that's spontaneous. But it's actually becoming more ordered. That's unfavorable. But the net total favors a reaction that is spontaneous because more heat was released than entropy being decreased. But let's look at an unspontaneous or non-spontaneous reaction. Let's say we are absorbing heat. So we have to add heat to the reaction. But the entropy is still in a disorderly fashion. But so much heat, much more heat was added that it becomes non-spontaneous. In this case, we add all this extra entropy, or the entropy, I should say, is decreased, even though that caused a little bit of heat, but not enough heat to overcome the non-spontaneity. And how about this last one? In this last one, we show we have to add heat. Heat is being absorbed. And also the entropy decreases, the disorder decreases. That, of course, is going to be non-spontaneous. Gibbs free energy, delta G, is the maximum amount of energy that can be coupled, meaning added together to another process to do useful work. So we have these reactions that occur. We can use that energy, that free energy, to do other processes. So when we couple it, we can add them together to do something else. Delta G, free energy, we can make it an equation as the enthalpy minus T delta S. And T is in kelvins. Now, if it's negative delta G, we have a spontaneous reaction. So that makes sense because remember, if delta H is negative, that's going to be exothermic. It produces heat. That's spontaneous. If we have a large delta S, large entropy, and we're subtracting something with a large entropy, that will be spontaneous as well. But if we have a large positive delta H, that's going to mean we have to make it very endothermic. We have to add a lot of energy for it to happen. And if this disorder is small, we're going to have a larger delta G. Chapter 18.5, the progress of chemical reactions, is a very quick section. Rate laws. The rate of a reaction will depend on the concentration of reactants. So let's say A goes to B. The rate, or how quick it is the change in A, how fast A changes to B, which is the concentration of A2 minus the concentration of A1 over the total time. Now that is proportional to the concentration of A. And if we have a proportionality and we want to make an equality, we're going to have to put a constant there. So that constant is K. If K is large, the products will be formed lickety-split very quickly. If it is small, products form slowly. This is a first-order reaction. In a first-order reaction, the reaction rate is directly proportional to the concentration of only one reactant. Now, when two substances react to give products, we have this equation. We have to include B. So we have the same thing here, constant. Concentration of A raised to the 8th A power, that's the coefficient, and multiplied by B, coefficient of B. So we can look to see what our Gibbs free energy is to see if something is spontaneous or non-spontaneous.